All right. Hopefully this works. Welcome to your last computer science class at Clark, which is kind of sad but also pretty glorious. So that I don't forget, I want to make sure to tell you just what a fantastic job I think everybody has done in this course. I think everybody's done an amazing job with, coming from 224 where things were new for some people, and working through all the ODPs and everything else like that, and it's been really cool to sort of watch the progress people have made and see where they've gotten to. And I've worked with a lot of you, one-on-one, and really seen your struggles and your growth. And I've watched the whole class, this section and the other section, really go from wherever you were to being solid programmers, and in my opinion, really well prepared for whatever you're going to next. Whether it's university, or more classes at Clark, or going into the job market or whatever. I think people are in really good shape. I think everyone's worked incredibly hard and done a great job of getting through all this material and learning everything that I wanted you to learn. So I want to thank you for your effort and for taking all of this as seriously and putting in everything that you put in. And I think it will be a fantastic journey for each of you down the road. So I just wanted to say that up front. And yeah, I kind of missed the ODPs too, because it was nice quick feedback for me from seeing where students were and that kind of thing. So but there's always ODPs in life somewhere. All right, so any questions before we just kind of jump into a review of the whole quarter? And so yeah, the morning recording did not take, so hopefully people from that section are going to catch this recording instead. All right, well, let's just talk about the final exam. So your final is on Monday, and it's at 2 o'clock. The morning section is at 10 o'clock, so it's your regular class meeting time. And you have to come to the section that you're actually enrolled in, okay? And it'll be similar to the midterm in style, so there'll be some questions where you're writing code, some questions where you're analyzing code and answering questions and so on. But in general, it will be where you're going to type stuff into a text area, right, and upload your answers that way. So exactly the same as the midterm, and the same comments as before in terms of if you want to write your answers up outside of Canvas and then copy and paste, I think that's a good strategy, because I don't know, Canvas bounces me out sometimes. I don't know if it does you. But don't be foiled by Canvas issues. All right, so I posted a list of kind of a synopsis of things that we've talked about this quarter, which are fair game for the final, but I haven't written the final yet, so not all of these will be on there, and there could be things in the final that are not listed here, but this is the bulk of what we've been doing. So and if you have questions that you want to jump to, shoot me a chat message. But from the top, basically writing code, analyzing code, answering questions about code, right? That's sort of the essence of the exam. And it's similar to the midterm in that way, right? So I might say, you know, write a program that, you know, makes a connection to this port number and, you know, reads one line from that connection and prints it out, right? And so that would be a program, it would be a class with a public static void main, and that would do, you know, everything that it had to do. I might say, show me a method that does such and such. I might say, write the code to implement a class that has the following characteristics. So, you know, an even class that has an even integer and lets you add and multiply or something. Similar in spirit to the programming assignments, right? But obviously not as long. It's a 1 hour exam. Okay, so I'll try to keep that in mind when I'm writing it. But basically, you know, be comfortable coding, be ready to look at code and answer questions about it. General concepts, right? The idea that Java is object-oriented, and what does that mean? This notion that you know, we don't like global variables, right? Because they are kind of uncontrolled. Anybody can read them or write them, and you never know what's going on with a global variable. Because even though your code may be very disciplined in this particular function, there could be 10 other functions that are interacting with this. So we take variables and we put them, you know, inside structures, for example, in C, right? Well, in some sense, we don't want global functions either, right? So we don't want, you know, anybody to just be able to come along and you know, interact with our data structure. So we take the code and we make that part of the data itself. So that's what we call an object, right? So it's really encapsulating data and code into this single entity, this single unit. Okay, that's kind of, you know, the one paragraph synopsis of object-oriented design for the purposes of 223 at least. You should realize Java is interpreted. Okay, we didn't do a lot with this, but it's interpreted, right? It does not compile down into the ones and zeros that your laptop CPU understands. It compiles to something called bytecode, which runs on a virtual machine called a JVM. The JVM is written in ones and zeros that run on your CPU, but if you have a different machine, you can write a JVM for that, and you can take the same compiled Java code, the same bytecode, and it'll run. So Java is highly portable that way. The trade-off is it can be slightly less efficient because, you know, there's this intermediate layer of interpretation. All right, so object-oriented approach to managing code and data. That's the bundling of code and data that I just talked about. Going along with that is the idea of information hiding, which is, for example, if I'm implementing a stack, the user has no reason to ever know about the stack pointer, right? The idea of a stack is you push things, you pop things. The first thing you pop is going to be the last thing you pushed, and so on. Stack pointer is part of the implementation, so my variable that acts as a stack pointer should be hidden from the user. Okay, so I would mark it private. And then if I decide one day I'm not going to use a stack pointer, I'm going to make a linked list to implement a stack, it doesn't affect anything. So information hiding and encapsulation, or this bundling of code and data. Those are sort of the two key prongs of object-oriented design. All right, no general Java syntax. It's not going to be, you know, a syntax exam, but you should be able to write if statements, for loops, while loops, declare variables, things like that, curly brackets, semicolons, case sensitivity, all of that stuff. So, you know, an occasional dropped semicolon I'm not going to be too worried about, but if the code that I'm looking at looks, you know, nothing like a Java program that a compiler would know what to do something with, right, then there may be points for that. So basic Java syntax, right, and it's so similar to C that there's probably not a whole lot to study there, except for some of the things that we'll talk about in a few minutes. Like defining a class, right? So that's a different thing, kind of unique to Java over C. So class declaration, right? The keyword class followed by the name of the class, and then inside curly brackets the whole definition of the fields, right, which are the variables, and the methods, which are the functions, right? and perhaps some constructors, which are special methods that don't return anything but are called when you construct an object. Okay, so when you define an object, right, so you have like a class rectangle, and it's got all the declarations for a class, the fields, the methods, and so on and so forth. In some other piece of code, you want to use a rectangle, so you can say rectangle, R5. Okay, that's a declaration, says R5 is a rectangle. But if I try to do anything with R5, like say R5.getHeight, I'm going to get a null pointer exception. Because declaring a rectangle is not the same thing as creating a rectangle. Right? This is clearing space on your bookshelf for a book. You can't go and read that book. There's an empty space there. You have to actually put a book there first. So we use the new keyword, R5 equals new rectangle. And you might pass arguments to it and so on. Now this is an actual rectangle, and I can say get the height, get the area, print it, etc., etc. So this is the declaration of an object of type rectangle. This is the construction or instantiation of the object. All right, you have to do both of those things, and you can do them in one step. I could do rectangle R5 equals new rectangle, and it's analogous to integer I equals 0, or struct node star root equals malloc. Right, declaration initialization, declaration initialization, declaration initialization. All right, and then we access the pieces of an object by just using a period. So, and I already did that here. Right here, I'm accessing a method, a function called getHeight, as part of this object R5. If I wanted to access a field, I could say R5.width equals 10, assuming it's not private. Right? This is a field, and this is calling a method, and it's the parentheses that tell you you're calling a method. When you call a method, in C, the name of the function is what tells you which function you're calling. In Java, you can have multiple methods with the same name, so we have this idea of a signature. And the signature is the combination of the name of a method and the types of arguments to it. Okay, so that's a method signature, and signatures also apply to constructors. So back to rectangles, when we wrote our rectangle class, we could construct a rectangle with a height and a width, pair of arguments. We could construct with just a single argument to make a square. We made a default constructor with no arguments that made a 1x1 rectangle. And so you can do different functions, different signatures, even though they have the same name. All right, static versus non-static. The only time in this course, I believe, that you've had to use the keyword static is when you're doing public static void main. Okay, we haven't talked about anything where you needed to define a static, but people have discovered statics, right? And statics are useful, but only in this one particular case, which is where you want to defeat the whole object-oriented mindset. Right? If you have something and you want it to be associated with an object, don't use a static. Okay? Static means forget about objects. I'm just making a plain old variable. It's not associated with this object or that object. It's associated with the definition of a class. So here's my class called stuff, and here's an integer I. And here's a static integer j. And so I can make a stuff my variable, and I can construct that as usual. And so I can say my variable dot I equals 5, and I'm talking about this this field inside this object. Okay, and I could do stuff your variable, and that could be a new instance of this class, and so I could say your variable dot I equals 10. Okay, there's two objects here. This object, the I field is equal to 5. This object, the I is equal to 10. Okay, they're totally different. But if I want to access J, that's a static, I would access that by saying something like the name of the class dot J equals 20. And you should not do this, but you are allowed to do it. I could say my variable dot J equals 20. Right? But you'll get a warning, I believe, from the compiler. And if I do this, and then you look at your variable dot J, it's going to be equal to 20, because it's really not part of your variable, it's part of the class. Right? And when I do this, I'm really doing this, and when you do this, you're really asking for this. So if you really want a global, right, that's one way to do it. But we really don't want globals when we're talking about objects. Okay, unless it's a very special case like a constant or something that you're positive you only want one value of. All right, and static methods are similar, except they apply to functions, methods, instead of just fields. All right, data structures. So, you know, we'll talk about arrays in a minute, but arrays are one type of data structure. Linked lists, trees, stacks, queues, hashes, all of these things, right? And in some cases, we built these things ourselves. Okay, we started off with linked lists, and we made those by making a class for the nodes and then linking them together like we did in 222. We made binary trees by defining nodes and writing recursive algorithms to search and traverse and so on. You made decision trees in one of your programming assignments, right, which is a different kind of binary tree. But we've also worked with built-in classes like linked list and hash map that provide data structures to us as, you know, abstract data types. So so I don't want you to feel like you have to memorize a whole lot for this exam, and you have pages of notes, and I'm not going to be like super rigid and say you can only have exactly 4 pages of notes, okay? I don't want you to spend the exam online downloading stuff, but, you know, if you want to make your reference sheets to describe, you know, the main methods inside the linked list class or the hash map class, right, that's fine. So this brings us to the idea of generics, right? So if you look at a linked list, the description of it includes this parameter, usually an E, which says we have to specify what type of object this linked list is comprised of. And when we declare something to be a linked list, we fill in that parameter. So here's how I declare a linked list of rectangles. And then when you construct it, that's the other time that you need to specify this parameter. So I can say my list equals new linked list. Tell me what kind of linked list you want to construct. And then if there's arguments to the constructor, you can put those after the angle brackets. Okay, now I have a linked list of rectangles. And, you know, the nice thing is that all of these methods work regardless of that. So if I want to add something to the end of the linked list, I can use the add last method as long as the thing I pass to it is whatever my parameter E was, in this case a rectangle. So they kind of work for free. So that's the idea of a generic. And some of these classes like hash maps and hash tables take 2 or more parameters, and so you just separate those with commas. And we can define generics ourselves. We didn't do a lot of that, but you basically put a parameter in the declaration of it, and then you use that parameter wherever you want it to be substituted. All right, iterators, we didn't do a whole lot with those explicitly, but we've been using them throughout. So think about a linked list, right? So linked list is this collection of objects. And we could make a for loop that says, you know, for I equals 0, I less than the length of this, and inside that loop we could say get element I, right? If we had a binary tree, we could recurse through a traversal of that, right? But that's not terribly convenient if what we want to do is, you know, when the user clicks the mouse, we want to print out the next element in our binary tree. Well, it's hard to wrap that inside a recursive traversal, right? So there's this idea of an iterator, which is basically this pair of things like has next and next. And so we started off by using this with scanners. We could basically say, while our scanner has a next token or a next line, give me the next token or the next line. And I can call these anywhere I want, right? I can construct the scanner, and then, you know, 5,000 lines later I can do this. And I can do this in, you know, different spots in my code. And any time that I say has next, it'll tell me if there's anything left to get, and if there is, I can call next to get it. So you could make an iterator to read a linked list. And basically each time I said next, it would return the next node in the list. Okay, and it's silly with a linked list in some sense, but with something like a hash table, where there's no natural order to the keys, the collection of keys in a hash table, we have to use something like an iterator if we want to loop over all of the keys. And so we can say create an iterator, and as long as there's a next key, get me the next key, and then we could use that to pick up the next data value stored, and so on. And so lots of these data structures, things that are called collections, right, and a linked list is an example of a collection, support the use of iterators. And it's a useful thing to know down the road, because it's a really powerful way to farm out data in anything other than a straightforward situation. Alright, strings. Know the basic methods associated with strings. So know how to get the length of a string, which is the length method. Okay, and that's different from the array where you just say dot length. For a string, you're actually calling a method. It's like string length, but it's called length. Equals, paren, tells you if two strings are equal. Compare to lets you know which string comes before the other. Character at lets you get the ith character from a string by passing, you know, the value I to character at. And remember, strings are not arrays of characters, right, to the user. They are internally. We saw that yesterday. But to us, a string is just a string, right? It's a type of object, right? It's a class. And so if you want the nth character, you call a method char at n, and it'll give you back the nth character. And all objects contain a toString method. Okay, and toString is what we use to convert an object into some sort of human readable form. Usually, but we can do anything we want with toString. But it's usually used to, you know, present some version of the object that looks like a string. All right. We do not use equal equal to see if two strings are the same, to see if two linked lists are the same, and so on. Equal equal says, are these things identical? Meaning, are they the same object? So two linked lists with the same values inside, but, you know, one is called list A, the other is called list B. If you say, is list A equal equal list B, they're not going to be equal. They're different lists. Okay. But we could have an equals method that we could write that would tell us, if they were comprised of the same elements. Okay, so strings come with an equals method, which says, do the strings have the same length, or are they comprised of exactly the same characters in the same order? All right, so arrays are interesting. So first of all, we have a few primitive data types. We have int, we have float, we have double, we have char, we have boolean, we have byte. We have these primitive data types that start with a lowercase letter, and they're not classes, right? There's a class named integer, which starts with an uppercase letter. That's a full-on class. We can find documentation for it and so on. But when we say int I, it's a special type of thing that we call a primitive. All right, so arrays of primitives are very straightforward. If I want an array of 10 integers, I can just do this, integer data bracket 10. And then I could immediately do something like data 5 equals 25. Okay, just like C, right? That's why it's like this. It's straightforward. But arrays of objects are different. So let's say we want an array of rectangles. Okay, so we declare it like this, rectangle data. That's the declaration. Next, we need to actually construct the array. So we would say data equals new rectangle 10. Now we've constructed an array of 10 references to rectangles. Right? We've declared an array that holds 10 things, each of which is a rectangle, but those rectangles do not exist yet. So if I say something like data bracket 5 dot get width, that's going to throw a null pointer exception. So there's a third thing that has to happen, which is you have to actually construct each rectangle that you want to use. For example, data bracket 5 equals new rectangle. Alright, so that's not a huge deal, it's just something to keep in mind. Primitives, we declare them and we can immediately use them. Objects in general, we need to declare the array, we need to use the new keyword to say how big that array is and actually create space for it. And then we also need to construct the individual objects in that array if we want to do something with them. So it's just got that extra step. Alright, so somewhere around here is where we switched, where we started the second half of the course. We were using scanners and print writers for standard in and standard out. But we can use them on other streams as well. So we can construct a scanner with system.in. That's how we read from standard in. We can construct a scanner from a new file. Right, and then we'll attempt to open this file and then create a scanner that we can use to read from that file, and then we can say, well, our scanner object has next line, we can say, string temp equals scanner object dot next line. And this can throw an exception, right, if you can't open that file for reading because it doesn't exist, or you don't have permission, or the directory doesn't exist or something, right, this will throw an exception. So we have to be careful with those. And we can also construct print writers for output. And we can do that with a file. And this will attempt to create a file with this name. If there's a path, it'll be in whatever directory that path points to. and if it can't construct it, it'll throw an exception. Otherwise, right, this gives us a print writer object, and then we can say print writer.println, and we can flush, and we can close. And scanners we usually close when we're done with them also to release the file. All right, so that's a way that we can read from and write to files, right, in the file system. And it's the same methods for the print writer and the scanner that we use for standard in, standard out. It's really just a difference in how they're constructed. And then at the end of the course, when we started working with sockets, this was how we were able to read from and write to sockets, right? We would construct a scanner, but instead of a file, we would use an input stream that we got from the socket. And when we construct a print writer, instead of a file, we use an output stream that we get from the socket. And then, you know, your actual calls to do the input and output are unchanged. And these are usually buffered, so if we want our print writer output to actually get sent right away, we can say flush. And it circumvents the buffering, and it says, okay, go ahead and write this stuff out now. Alright, class extensions. We did this with things like J-frames and J-panels, and eventually threads. So any class can be extended, unless it's marked final, like string. So we can make our own version of a class by saying it extends a base class or a superclass. And then we basically have everything that's in the original class inside our new class. But we can add additional fields, we can add additional methods, or we can override fields or methods that we inherited. Okay, and so this is what we do when we extend a JPanel and we write our own version of paint. We're overriding the JPanel's paint method. But we're getting all of the other stuff that was in a JPanel, and we're keeping that intact unless we override that as well. And if we want to get to the base class's method that we've overridden, we can use the super keyword to access that. So if we want to do something from the base class like paint, right, we can say super.paint, which is what we do in the beginning of our paint. All right, exceptions and exception handling. So we've only done this with try-catch blocks. Okay, you can also handle exceptions by declaring that a method throws an exception, but we have not done that. Okay, and I won't ask you about that. If I do anything on exceptions, I'll ask you to make try-catch blocks. And like other things in Java, right, it's just we can put a set of statements inside this block. We can make a catch statement, and we can name a type of exception in here and pick a variable to be assigned information about that exception, right? And if an exception occurs in this try block and it matches the type of exception in the catch block, we'll jump down to here and we'll start executing. And this object that we name here, which is typically E, will be an object that's associated with the exception that occurred. And we can have multiple catch blocks with different types of exceptions, and then there's an optional otherwise block. And the otherwise block is called either when the try block finishes or when the catch block finishes. And then you just continue on normally. So it's the standard mechanism for dealing with things that go wrong. Main mantra for try-catch blocks: keep them tight, right? Don't just put your whole method inside a try-catch block, unless you're teaching the course and you're lazy like me. But try to put the blocks around, you know, the smallest set of code that could throw an exception, because usually, if something goes wrong, you want to do something based on what particularly went wrong. Right? Did I have a problem opening the scanner? Did I have a problem closing the scanner? Did I have a problem reading from the scanner? So try to be pretty nuanced with those. All right, swing and GUIs and window builders and all that sort of stuff. So window builder creates a lot of code for us. Right? If I double click on a button in Eclipse, it creates this whole mouse listener and this event listener and drops me into the editor surrounded by code that's already been written for me. I'm not holding you responsible for being able to write that code yourself. Okay, the code that's auto-generated by Eclipse in that case, I'm not going to ask you to write. If you right-click on an object and you say add, an event handler for mouse motion, WindowBuilder creates a bunch of code for you that describes, a motion listener and sets up the implementation and so on, right? I might give you that code and say, fill in your code to do the following. Okay, so I could say, I want you to set something up so that when a person clicks their mouse, a rectangle is drawn at those XY coordinates. Okay, but I would give you a template of the code and say, here's the mouse listener code and so on and so forth. But I'd want you to be able to work with that. And, in that particular example, read the XY coordinates from the argument to the mouse listener, save them somewhere, call the repaint method, and then in the thing that you're repainting, the paint method there should look for those saved arguments and use that to draw a rectangle. So be able to override the public void paint method, set things up for later painting, right, and so on. And then, understand the concept of these event handlers, these listeners, and so on. The fact that this is event-driven code, the notion that you should not do an infinite loop inside one of these, and you should not do drawing directly from inside these. You should set things up and then call repaint. Okay, that was sort of the punchline of all of our GUI stuff. Threads we have done by mainly extending the thread class. So make a class, super cool class that extends thread, and then inside that class I can make a run method, and then if somewhere else I construct one of those, an object of that type, and I call it start method, it'll do two things. It will create a new thread, a new process, and then it'll call the run code in that new thread. Right? So I make a thread, something that extends class thread, I write a run method, and then when I want it to run in a separate process, I simply call the start method. And the start method creates a new thread and then makes a call to run. And sometimes we need to share information between threads, and there's a number of ways to do that, but mostly it's about passing the identity of one thread to another. So if our main method is creating a thread, and we want that thread to be able to make reference to something in the main method, we could pass the keyword this, either to the constructor of a thread or to some method in the thread, so that the thread can remember, the value of this, which is me. It's the main method's identity. And so we can have a main method that's running, and this is actually a thread, and it could create a second thread, and maybe it creates a third thread, and this thread might create another thread. And you can have all these threads executing, and it may be that there's some method inside here that each of these threads wants to interact with, right? So when I construct this thread T2, I would somehow give it access to this method, right? Maybe in the constructor I would tell it who I am, and it might do the same thing when it constructs T4 and so on. But there's a danger that maybe this code is something that should only be run at once at a time. Maybe if two different processes are executing this code simultaneously, bad things will happen. Right? Perhaps this reads the value of a variable, does some updating, and then sets the value of the variable. And I don't want another thread to come in and start modifying this information while some other thread is modifying it. So we can control access to these shared objects, and that's the whole idea of the synchronization. So I could take a set of code in here and I could say synchronized, and then as long as as one thread is executing this set of code, no other thread will be able to start executing this because it'll say, wait, this is synchronized. Okay, so that's a good conceptual thing to know. And so that has to do with resource sharing, which is tied into the idea of deadlock and live lock, which are basically two or more processes waiting for resources that the other has in a way that neither can get what it needs to continue its progress. So if you have two processes and they each want something the other one has, they're deadlocked, right? Neither can make progress. If they release their resources periodically and try again and they keep getting locked, right, that might be a live lock situation. But the punchline is the same, they're basically stuck. Your whole system will just stall out. And it's a typical problem when you have parallel processing like this. Alright, and then last real topic was networking. So know about the client-server model. Okay, client is the thing that makes a request to a server. The server exists first and is locatable by typically a port number. And then the client comes along and asks for a connection to the server. And once that handshake is set up, they start exchanging information and doing whatever it is that they want to do. And so in Java, it's a very specific pair of options. You can make a server socket, which you construct with a port number, and then you call the accept method, and that returns a socket. Okay, so that's the server side. On the client side, the server socket is already out there waiting for a connection. So I construct a socket, but I do that with the address of the server and the port number. Alright, once I do this, this socket and this socket are connected together. So that's the whole setup. And the main difference is on the server side, you create a server socket, you just specify the port number. You don't have to specify a machine address because it's on the machine that you're currently running on. And you have to say accept to say, let me get a connection from someone. On the client side, you have to specify not only the port number, but the address where the server socket is located. Which machine are you trying to talk to? And this, once it reaches the server, if the accept call is waiting, and it's accepted, then this comes back and you're given a socket, and those two sockets are connected. So if we want to write to the socket, we can say get output stream, use that to make a print writer. If we want to read, we can say socket.get input stream and construct a scanner from that, and then you're off and running. And there's lots of places for exceptions to be thrown. So and that was where I usually got really sloppy and just sort of put a try catch around the whole construction of the socket and accept and all of that stuff. And we use client model all the time. When you make a PuTTY connection, PuTTY is the client, the SSH daemon on the Linux machine is the server. Okay. When you ask for a web page, Chrome is the client and the web server that you're connecting to is the server. Right, so this is the model that we use all the time. Alright, know how to write comments. I'm not going to require comments in your code, but if you're unsure how to do something, put a comment in and tell me what you're trying to do. Right? I want to know if the strings are equal, but I don't know if this equal works. Right? At least let me know that you had some doubt about it. Or, you know, I want to add to the end of a list, but I don't remember what the method is. Okay. Well, that's fine. You could look that up, you know. But now I know you're trying to add to the end of the list, which is probably the key. All right, that's the whole course in 50 minutes. So I have office hours today at 3. I posted some office hours for next week. They're not at the same times that they've been. Okay, they're mostly earlier in the day. Monday through Thursday, and then Thursdays the last day of school. But we have our exam Monday, and then we're done. So, but I'll have office hours if you want to come by and talk about net dots or anything else. So yeah, thank you again, everybody. It's been educational for me too, and it's certainly been a year that I think we'll be telling people about 20, 30 years from now about, oh yeah, that was a strange year, let me tell you about it. And it just keeps getting stranger. But we made it through, and that's fantastic. So have a good rest of the day. Have a great weekend. I will see you on Monday. I'll be in the regular Zoom classroom for the duration, so if you have questions during the exam, you can just send me a chat message. And there you go. That's it. All right, so thank you, and have a good one, and I'll see you later.